Good morning, everyone. My name is Michał. I work at Reality Games, where we are building games based on big data. And today, I want to talk about separation of concerns. How should we use functional programming tools to perform separation of concerns? And we'll be using free and tagless approach, which have gained lots of traction recently. So I will be building on top of what you've learned so far. There will be lots of code, as I said before, live coding. But what's important, what I want you to take away from this session is the concept itself. So what do we really need in order to achieve separation of concerns? And I will start by defining the separation of concerns by defining the opposite of separation of concerns. So where is our intuition when the separation of concern is not there? You've probably been in a situation when you just wanted to do a quick fix or add a simple new feature, and you ended up, after a few hours of coding, you ended up with this git status like that and lots of failing tests. So that means that you didn't have separated concerns, you did have entangled concerns. And this is a large, big problem which has been with us since many years ago. In 1974, Edgar Dijkstra wrote a paper about separation of concerns, and he defined this intelligent thinking approach. So this is kind of intuition for us. How should we think about our software? So when we are able to think about aspects, isolated aspects in isolation from each other, then we can really have separated concerns. So we've been struggling a lot with that. And so this is an antidote. Intelligent thinking is antidote to separation of concern, but it's still not there. What kind of tools we are using in order to think intelligently? We are using whiteboards, right? Software architects use whiteboards and boxes. So this is the tool that we are using, and this is the tool I will be using in this presentation. So for example, when we have a software, we want to divide it into concerns, right? So business concern number one, high-level logic, things like that. So those are the boxes that we are really drawing on our whiteboards. Intuitively, we know how to split those concerns. So for example, logging metrics and DB access are technical ones, business ones are dependent on the domain you are using. And there's also one more thing we are using. This is arrows. In this case, I'm using arrows as knows about kind of semantic. So high-level logic knows about business concern number 2 and 1, and knows about low-level logic, which in turn knows about logging metrics and DB access. And of course, logging doesn't know anything about metrics. So this is our ideal approach, right? Whiteboard approach. And in Scala, we can encode that knows about arrow as imports, right? So if you have a module and you have 10 imports to different kind of modules, that means that you have 10 outgoing arrows. And what we are aiming for, we are aiming to have as many components as possible without any outgoing arrows, so without any outside knowledge. So this is intelligent thinking, as Edgar Dijkstra described that. So business number 1 doesn't know anything about anything else, so that's how can we think intelligently about this business concern. So it's pretty obvious, right? But somehow we are still not there yet. So Edgar Dijkstra told us what to do. We have whiteboards where we can draw our architectures, but we are still not there. One puzzle piece is missing. And in order to know what this piece is, let's imagine that we are landscape designers. So we are designing this park as a landscape designer, and we designed this little circle spot in the middle of the pavement. But then the real life kicks in. People start using that park, and some of those people are in a rush, and they take shortcuts, right? And the whole park experience deteriorates for everybody else using that park. And of course, it infuriates the park designer, landscape designer. The same happens in the software. So when you think about that, we are designers, and we intend our developers to use the park, the software that we designed, in a particular way. But we somehow end up using those kind of shortcuts when we are in a hurry, right? So this is like high-level, low-level logic, business number 1, and then DB access, but we are in a hurry, so we just go straight to the database. And the whole software module experience deteriorates for every software developer there. So the one puzzle that's missing is developer experience. So we need to be able to create our software in a way that still constrains our design. Not only the code, the functions, the modules, but also the design of the whole software. And this means that those tools need also to constrain us, even if we are in a hurry. And there are many tools like that. The one that I want to talk about today is a free monad. Free monad is a type. Is a type that we can use. So whenever you can see a function that returns a free of f and a, that means this function returns a description of a program that uses operations of type f, for example, a seed trait with some kind of operations. And when this description program is run eventually in the future, this will return the value of type a. So this is free is just a description of a program, not a real program. So just the value that describes that. And we'll try to use this free monad in a non-trivial example, as I promised. So we'll use prisoner's dilemma, which I will describe in a moment. Then we'll create a free applications with 15 overlapping concerns, and we'll use cats and freestyle to do that. Then we'll move towards more freestyle stuff and briefly talk about tagless final. So that's the journey that we will have in this talk. Prisoner's dilemma. 40 minutes, so let's very quickly recap what prisoner dilemma is about. So we have two prisoners who are captured and isolated, interrogated in isolation, and both of them have one question to answer. The other one, is the other prisoner guilty or not? So each of them can remain silent or rat on the other friend. So we have four approaches, output, sorry. One output is that both of them say the other one is guilty. They get 3 years in jail both. They can remain silent. They will get just 1 year both. Or, of course, they can rat on each other. In this case, when one of them rats on the other one and the other one is silent, then the one that ratted walks off freely and the other one gets 3 years. And in the other direction, the same thing. So this is a very simple game. And if you play it once, it doesn't really matter. But there has been lots of research about that, and this has been used as a model for our behavior as humans. For example, General Stanley McChrystal used that to reorganize his special task force team in Iraq back in 10 years ago, something like that. So use prisoner's dilemma to reorganize so that the whole task force becomes more agile and can really use this kind of approach of being flexible in the different situations without this command and control approach. And Nicky Case created the Game of Trust. The Game of Trust is a game you can play in your browser, and really a game of trust is prisoner's dilemma in disguise. And so, for example, lots of research was about that. So we are playing games of prisoner's dilemma. Lots of them have algorithms and that play the game with a strategy, because you know when you played with the other person before or not, so you can base your strategy on how many answers, guilty or silent, did you get from this particular person, and so forth, and so on and so forth. For example, the winning algorithm for now is 4 lines long. We can talk about that later on. It's not a soft talk, it's a technical talk. So let's move to the prisoner's dilemma. We'll try to create a whole infrastructure to play repeated prisoner's dilemma games using free monad approach. So let's start with the first application. First application is hot seat game. Hot seat means that we both players are sitting at the one table, one computer playing in a console game like that. For example, my name is Adam, hello Adam, and the other one is Jane, hello Jane. Then they are asked about their decisions, whether the other one is guilty or not, and then the verdict is provided, right? So very simple game, console game. Let's try to implement this game first in a real, normal, simple Scala. So this is how it would look like. First, we need a function to meet the prisoner, which just reads line and returns a prisoner with a name. Then we need a prisoner's decision based on the read line from the console. Then we need a very simple function to create a verdict based on those two decisions. This is the encoding of what I've shown you before. And of course, we need to give it a verdict. So very, very simple 4 functions, which can be reused to create a real game. So this is one slide. The whole game is on one slide without the implementations. So the signature and the 6 lines at the bottom is the game, right? So we are meeting the prisoners, getting the decisions, and then providing the verdict. So the question for you is, how many concerns does this simple application have? 1 concern. Who is for 1 concern? 2 concerns. Okay, several people. 3 concerns. 4 concerns. 5 concerns. Okay. For sure, there is 1 concern, which is a hot seat logic, the logic of the game, right? So we are meeting the prisoners, getting the answers, and creating a verdict. So this is the step-by-step sequence algorithm. But also, we have 3 other ones. So 4 was the correct answer, in my opinion. We can talk about that, about different ones after the talk. But for me, is that there are 4 concerns here. So we are computing the verdict concern, which is this pure function, right? Getting the 2 decisions and then providing the verdict. And player interaction, that means that we want to ask players something and we want to get decisions from them without concerning ourselves with the technical implementation, which is the 4th concern, player communication using console. And the next quiz is, how many of those concerns are isolated, separated, in your opinion? So remember, I provided a very intuitive definition of that using this diagram. No outgoing error. That means that in this case, only 1 concern is truly separated. We can think intelligently about this particular concern because it doesn't really know about anything else. This is a pure function. Then the next question is, sorry about so many questions, but the next question is, how many concerns can we really have here in this application? Using free monad, we can delete, remove those 2 arrows and create another separated concern, which is a player interaction. This is the whole thing. Even in this simple scenario, even in this simple application, we can have 2 separated concerns using the free monad approach. So this is something that I want to do and show you right now. So again, first concern is a computing verdict. So verdict, simple, pure function, nothing fancy. And second one, the second concern is using free approach. So we are disentangling the player interaction from the console implementation. And as I said, free monad approach is something like that, a little boilerplate in Scala. So we have a player, sealed trait player, which is player operations, and free extents. That means that we have 3 possible operations. Meet the prisoner, which returns a prisoner, get prisoner, which returns a decision, and give verdict, which is returns a unit, because this is kind of effective kind of thing, right? But those are only like semantic descriptions of what we want to have. And in Scala, we also need to deal with those this boilerplate at the bottom. It doesn't really matter for this talk. I will tell you about how to deal with that at the end of it, but this is a boilerplate. Please don't be concerned with that. The only thing that matters is this kind of encoding. So let's, given that, without any consoles and things like that, just the player interaction, we can create a program which looks very similar to what we've seen before in the simple case, but we are using for comprehension. So that means that with pure no effects, just a description of a program, nothing more. Very similar. And now, only then we can deal with the 4th technical concern. The 4th technical concern is interpretation of the player operations, those 3, meet prisoner, get decision, give verdict, into I/O. I/O is a description of impure effects. So, for example, this is how it's defined in Cats effects library. So as you can see, it gets some kind of block of code which is lazily evaluated at the end of the world when the program is really executed. So we can put something in this I/O, and we know it won't be executed until the end. So we can use that in order to provide the print lines and read lines inside. So when we are interpreting it, we won't be really printing or reading anything until we really want to. So this is kind of approach that's pretty simple and can be used anywhere in your code if you want to have control over your effects. And this is how we interpret things into a console. So we are interpreting free. This is a pattern matching in free monad approach using cats. This is thing that we do often. So we are interpreting meet prisoner into say, here, and say. So print line, read line, and print line, IO, and then getting the player decision. Very similar thing. And give verdict is just one line of code. This is print lining the verdict, right? So this is the technical concern. So we are now interpreting the player interaction concern, which is a business one, into a technical one. And this is how it looks on the whiteboard diagram. Pure function is a separated concern. Hot seat logic is a free of S and unit. That means that this is a description of a program that uses S and returns a unit. And the player interaction uses player operations to return A, and player communication using console is an interpreter from player operations into IO. Red means that they are separated. So two separate concerns. And end of the world. So we have those separate concerns which don't know about anything else, and we are connecting all the dots at the end of the world. So we have this program, which is a free, then we are interpreting it using fold map, using the interpreter, this pattern matching interpreter we just described, and we get IO of unit, and then only then we run it at the end of the world. So this is when the print lines and read lines are really executed. So we have a unit as a return type and some side effects. And the boilerplate problem that I didn't want you to be concerned about is something that can be quickly dealt with using this Freestyle library, which uses cats free, but provides a nicer encoding to that, because this is how it looks using Freestyle. So we are just having this at free rate, and we describe those free operations as defs. At the inside, it's just what I shown you, but it looks nicer for the developer, right? To not be concerned with this all this boilerplate. So from now on, I will just show you all the examples using Freestyle, and in a bit I will show you how those macros are really extended and how they look similar to what I've shown you before. So this is the player. Free operations. The handler is an interpreter in style nomenclature. So this is how we interpreting player into IO. So by overriding the methods in the handler, which are provided by Freestyle, meet prisoner, get player decision, give verdict. The same thing, but maybe in some kind of nicer wrapping, right? But much cleaner for the reader. And now let's simulate a real life. That means we have this small application. The hot seat application, 2 players can play on one computer. And now let's simulate playing with a bot, right? Because the same game can be played with some kind of bot. So let's try to simulate this kind of approach. This is how the program would look like. So hello, Michał, and here's Wally. Is he guilty or not? And then we get the decision and the verdict for me based on the bot, right? So the same program, the same kind of questions asked. So lots of concerns that can be duplicated and entangled together. But by using the approach, we are able to just add more code without rewriting anything that we've written so far. And I will show you how to do that. So this is our diagram. We have this player interaction and player communication using console. What we need more is some kind of unknown opponent logic and interaction. Unknown opponent means it can be a bot, it can be a player over network, it can be a bot over network, whatever, right? So unknown opponent. What we know in this program is that there is a local player and plays with unknown opponent somewhere out there. So we need a new set of operations, new set of operations to play with an opponent. So meet opponent and get opponent decision. This is the 2 operations that we will need in order to create this program. Okay, and the program itself will look like that. So we will first need to meet the prisoner, then we'll need to meet the opponent, and then there is this blank that I want to fill in right now. So let's. Okay. So this is what we have right now. We have those 2 operation sets. As I told you, I will show you how those macros are extended. So we have this player, meet prisoner, get player decision. This is how the macro is expanded. So yeah, lots of code, boilerplate, but the trait is here, and those extends are over here. So it looks very similar. It has some additional magic that will help us later on. But this is some kind the thing that's really very simple to write when you are boilerplate. Happy with the boilerplate in your code. If you are not, please use Freestyle. And the second one, the opponent, looks very similar: meet opponent and get opponent decision. So let's write the program itself. So we have a player, we have the opponent, which is a option of prisoner, because this is unknown opponent. It may not be there. So what we need to do is we need to map over it, and we'll map over to a program. So we will be mapping an opponent inside this option into a program. So we'll be creating a program if we have an opponent. So what we need first is player decision. So we'll use get player decision, player and opponent. So this is something from this trait, player trait. Then what we need next, when we get the player decision, what decision do we need next? Opponent decision, thank you. And we'll be using an operation from the second trait, from the second set of operations, opponent. And then what we can do is, of course, we can give verdict, but we can give verdict only to the local player by providing player, by using this simple function, this pure function, player decision and opponent decision, and we can yield a unit because we don't care about what this program returns. So will it compile or not? What's your opinion? What do you think? Yes? No? Okay, let's check it out. No wins. Why? What we did is we mapped maybe opponent into a program, right? So, but we need a second case. We need what happens when there is no opponent. So the compiler helped us with that. Get or else, what we need to do when we have no opponent. How can we play the game? So we can play a local game, right? We can do that. But in this case, let's just run the program again. So we'll just run the whole thing again. And now it should compile. Yes, it compiles. Let's run it. Single player up. Yeah, what's your name? And is R2D2 guilty or not? What do you think, guys? Yes, I'm trustful a person, and I'm staying 3 years in prison, and R2D2 is free. Unfortunately, yeah, it happens. And what's important here is that if we have separated concerns, we can have tests for all those concerns, right? So, for example, without any technical concerns, I can just run this test and see whether my program is okay or not, right? The single-player program without console, without anything like that. All the concerns I'm talking about are tested in the repository, and you can check this out. Okay, let's go back to this to the presentation. So what we did is we just created a map over this maybe opponent, created a program, and if there is no opponent, we just start over, and that's all. So the whole program fits on one slide, and this will happen a lot more in this presentation. So when I first shown this example to my friend, this is what he sent me back on Slack. Yeah, so I understand. This is something I also discovered at the beginning of my journey. But then I thought about it, and when I see this for comprehension, yeah, it may look ugly at the beginning. But then when I got used to that, whenever I saw this for comprehension, I probably knew that somebody was trying to disentangle the concerns, right? So this is a pure approach to something that they wanted to describe. So yeah, it may look ugly at the beginning because we are not really used to that. But after some time, you can really get some conclusions out of seeing this kind of code. Somebody was thoughtful enough to write this in this way to disentangle the concerns in the code. So maybe it's worth getting used to that already. And then in the application itself, we have this player handle, which is a console handler, right? Print lines and read lines. And then we have this new application, unknown opponent. It won't compile. It will tell us that something's missing, because we have this player interpreter, player to IO, console print lines to read lines, but we don't have this opponent operations interpreters. So compiler will tell us that we are missing a crucial bit in our software application, that is how to technically interpret the opponent operations. So this won't compile, so we will need to create another interpreter. Anytime you see something like that. So there is an interpreter missing. We need to create a bot stateful interpreter. I'm using var here to show you that you can use anything in your interpreters if you want to. So there's a var with some kind of strategies for different bots, and meet opponent and get opponent decision are interpreted into IOs, but inside those IOs are, you know, crazy things like vars and things like that. That's possible. Then we can just implicitly define this opponent handler, and this will all compile. We can unsafely run it at the end. And our application, this is what I've shown you during the live coding when I played with R2D2. And this is the whole application. So, and again, we are just connecting the dots which already have been there. And the workflow usually goes like that. So we first define the operations, semantically think about those operations from the business levels, and then create programs using that. Also on the business level, we don't really care about any technical details. And only then when you try to run them, we start caring about technical details and are fixing errors by implementing the interpreters. So this is why this tool is so useful. So again, can we have a different interpreter for opponent? Of course, the answer is yes, we can. We will try to implement the game over the network. So we'll reuse the same logic, like unknown opponent was done for that, right? Unknown opponent is so that we can play with unknown opponents. That means bot, which we already implemented, or a remote opponent. So there will be another interpreter, remote opponent, second interpreter for this set of operations. And we'll use Akka remoting to do that. So this will be really over the network. But until we really, the first step in the workflow is technical concern. So Akka remoting will be done as the last step of the whole thing. First, we need to define how to connect two players over something that is like a network, no matter what the network looks like. So we need to first define the algorithm for this thing, right? How can we connect two players who don't know each other? And this is one of the approaches. So we can have those two players register as waiting, and then get waiting players. If there is a player waiting, then we join the player. If not, we are repeating the whole cycle. And of course, the one that register, if it can see that someone registered for the game, it just starts the game because those two opponents have found each other. So this is one of the algorithms. There are many other ones, and this one has some problems. But semantically, we are just talking about semantics. And if we are talking about semantics, we can just create another set of operations for matchmaking. So those 5 operations here are encoded as a free set of operations, right? So set of operations to be used inside a free monad. So registers waiting, unregistered waiting, get waiting players, and so on and so forth. So 5 operations that we can reuse into this kind of boxes. Wait for opponent and find opponent, right? And again, there is nothing here about Akka remoting, about TCP, sockets, and so on and so forth. So we are just creating programs that on semantic level are algorithms for the network players. In this case, again, a program that fits on one slide. This is a program for finding an opponent. It needs a matchmaking ops and timing ops, waiting for players. Then when some players have been found, we are getting the first one, joining the player, and if not, we are trying to wait for another opponent. Of course, this is all those functions return free, so we have free in free, returning some free. So this is the semantic level, right? Again, just algorithm without technical things, and the compiler will guide us to do the right thing. And we can test the algorithm without creating any servers, and so on and so forth. So this is kind of thing that we did. And then let's focus on the main objective, which is remote opponent. So what we wanted to do is to create a remote opponent, right? And we got some on the side way to create a matchmaking algorithm, but this doesn't concern what we have here. So we need to connect those two things. Again, this is how bot stateful handler look like. Yeah, so we had this meet opponent and get opponent decision using var map for the strategies. And now we have to create another handler, but for this remote opponent operation set. So meet opponent and get opponent decision, the same two operations will be interpreted into something different for the remote opponent case. What's that? The last time it was IO, and right now we can reuse this matchmaking things that we did in isolation. We thought intelligently about them, and now we can reuse them. So this is a one-liner. We are just interpreting into free now. So we are interpreting a remote opponent into free. So we are interpreting a free program into another free program. And this is how we connect the matchmaking, which we thought about intelligently in isolation, and remote opponent handling, which we also defined in isolation. So those two things are connected here. And again, when we get back to the workflow alone, the concept is that if we miss some interpreter at the end, the compiler will tell us. So let's see what would compiler tell us in this case. We had opponent interaction, meet prisoner, meet opponent, get opponent decision. We implemented unknown opponent logic game using that, and bot opponent with this vars to handle this opponent interaction operation, right? Technically. And now we need this remote opponent, which we interpreted into matchmaking programs. So what we are really missing here in this whole puzzle is one technical concern, how to implement matchmaking operations, those register as waiting, get waiting opponents, and things like that. So let's zoom in. This is where Akka comes in. So this is remote actor matchmaker matchmaker concern. This is the last step of the whole program. We tested the algorithm, we know it works, we tested the game itself, we know it works, and now what we really are missing is how really to create the layer, the network layer for that. So this is the set of operations, and what we are missing right now is a handler, right? So just a handler that will use Akka. And handler, in this case, is very, very simple. Again, this is just sending messages to the server over the remote connection and getting some ask server for get waiting players. So again, a very, very simple handler. All those things, there are many files in the project, but every file is like 20, 30 lines max, and usually it's just 10. So very, very small components which we can test in isolation, think about in isolation. And only at the end, we are creating programs, also very small programs, again, at the end of the world. We are just interpreting the same program, unknown opponent, into a free, as I told you. Then we are interpreting this free into IO, and only then unsafely run it synchronously. So this is when all the magic happens. This is when the servers are really created, the actors are really created, the print lines are done, and so on and so forth. So this is our whiteboard. This is how it looks like free game mode, single player with bots, hot seat game, and multiplayer game using Akka remoting. Lots of tests for each of those concerns, and end of the world applications, the three of them. I didn't show you everything, but the most crucial parts have been described. Can be overwhelming, but as I said before, there are very, very small pieces, and you can go to one piece and see how it works in isolation, and only then you can connect those dots. So you think about those small components in isolation, and then you think about the connection between those components in isolation. That's how it looks like. Note that we didn't really change any code. Right? So this is the approach. This is the approach that is possible. You are just adding new modules and connecting because they are very, very small. So that means they are more reusable. All right. So we addressed this problem with free, which was boilerplate, and the boilerplate can be dealt with using macros. But there are several more problems. If you've never used free, I want to just make sure that you know what to deal with. So we use this kind of modules in order to compose sets of operations. This is a freestyle approach, and this is a free approach. And the freestyle approach, you don't care about the order of those 4 things. In free, you need to care about that, because compiler will be very unhappy when you miss some of those orders, and of course the compilation message will not help you, as you probably know. So in this case, you don't care about it. In this case, it can be a very problematic way if you start composing those things. So this is a free in Cats. And the second problem is that the free monad approach creates lots of objects. So it's very GC heavy. And that's if that's a problem in your application. It may not be, but if it's a problem, then you probably should be using tagless final approach. And in Freestyle, you have something like that, and it's very, very easy to use. So we had something like that. A mid prisoner returns a free, right? So creates a value that describes a program. This is a free monad, free value, and using set of operations S, and when run, it will return a value of prisoner. And in final tagless approach, what we are doing is we are not creating this value. We are just abstracting over using F. And this target monad is being chosen at the end of the program when somebody wants to run it, right? So it may be something else than free. And in order to create this set of operations, instead of using add free, you are using add tagless, and that's all. And of course, this will have some problems. I will briefly talk about the summary of those problems in a bit. But usually, from the perspective of semantics, separation of concerns, it doesn't really matter whether you use free or tagless. It's just a technical concern that you need to be aware of, right? So again, course of action, in case nobody. In case you want to dive into that kind of approaches, I suggest you start by using directly Cats or Scala Z free with the boilerplate and the compiler errors and so on and so forth to learn how those things work together. And then, only then, play with the final tagless directly, so you are aware of those technical concerns. And when comfortable, start using Freestyle. It's very, very quickly evolving library. Recently, they added a Cassandra effect to that, so you can really create a free kind of programs for different use cases in your application. I encourage you to look at that, and then you will be able very quickly to change tagless into free and free into tagless based on those technical concerns. Like those two. This is a abstraction talk, the semantics kind of level talk, and if you are really concerned with this technical things like why should we use free, why should we use tagless and not the other one, I encourage you to look at this blog post by Adam Walski, who really compares those two approaches, and the snapshot of the summary table he provides there is here. So in free, program is data, and tagless is an expression, and that means that we have some additional properties in both cases, right? For example, in free we have stack safety, and in tagless we don't have a GC heavy programs. So something to look on when you are comfortable using both approaches. And all the code I've shown you here is on the GitHub. 3 prisoners, 6 applications, because I implemented using free approach and freestyle approach, those 2 applications, so you can look how do they differ, where's the difference, and there are tests for both of them. So this kind of reference implementation, how to use this approach using Akka servers, Akka remoting, and all the impure things. So whenever you are concerned with some blog posts about free monads or talks, please have a look at this repository when the simple application which really works is implemented. And using tests, state monads, and things like that. So please use it as a reference implementation. Again, my name is Michał. I work at Reality Games. If you want to see the games are we up to, if you want to talk about Prisoner's Dilemma and all the soft things or free monads, just grab me in the hallways. I'm here until the end of the conference. And this is my blog, this is my Twitter handle, and thank you very much for your attention. Are there any questions?
Thank you for the great speech. Usually we are solving this problem by inverting dependencies. In your approach, you are building the program AST and then interpret it. And in inversion of dependencies, we are just passing some traits to our program, and when it runs, it uses some abstract implementations. What is better in your approach?
When you're using interfaces, you can't really easily use the effects inside those interfaces. So when you want to, for example, you have this meet opponent, in my case, which can be a network, can be a local var, and the player, which can be a console, and its local can be a network. When you want to mix them together using this interface approach, the standard object-oriented interface, you need to choose only one effect. It probably will be the most powerful one, unfortunately. So for example, an async one, right? So you will be doing console reads and writes using asynchronous code. In this approach, you won't have to.
We can try to use IO monad, for example, to abstract all the effects.
Sure. And this way you move towards final tagless approach without freestyle. Yeah.
But final tagless requires a lot of boilerplate or microses or all the things doing under the hood. And if we use IO monad, it's just Scala code. It's very
the final tagless won't really. The boilerplate is just about free monads. So the final tagless approach is pretty simple and natural one for many. So it's just a fancy name for what you are describing.
Oh, thank you.
No problem. Any more questions? One more question. Okay.
Hi, a very good presentation. Can you please show one more time free annotation in your code?
All right. Free annotation.
Yeah. It's a macro annotation, yeah?
This one.
What you typed to see the macro expansion?
Okay. You see this icon here? I'm using IntelliJ.
IntelliJ has
expand macro, yeah. You can use that. You can use that also in your macros.
Debugging macros is painful. Actually, it's very useful. Thank you.
No problem. One more question over here.
I actually had more than one question, but I guess you sort of answered one of them. But just to reiterate, start with that. So you mentioned like you can tag that with free or tagless, right? And you said like you kind of don't care about what goes there because the boilerplate like specific to free or tagless will be generated for you. And my question was like, so why do I care at all, right? And you kind of answered that for tagless there'll be less GC pressure than for free, and
yeah. So
like maybe you can elaborate.
Thanks for the question. So using Freestyle, you don't really care about that because there's a magic that can connect those two worlds together. But when you are using just normal Cats versions, you need to be aware that it's very hard to connect those two worlds together. So you either choose the final tagless approach or free monads in your module. This is the most straightforward way, unfortunately. Using Freestyle is better to mix those two worlds together if you really need to.
Okay, and talking about this separation of concerns, and if you can open your slide where you doing like maybe opponent.
Mm-hmm.
So
sure. Yep.
Yeah, so isn't it like you kind of mix in here different concerns, like okay, there may be opponent, maybe not opponent, then you also like run something. So how would you
of course
the other way? I mean,
thanks for the question. So this is I need to stop somewhere, right? And probably we can all argue that this already this one is mixing 2 or 3 concerns together. That's why at the beginning, when I asked you about those concerns, I was smiling a lot because there were people who convinced me that there are only 2 concerns there, or 5 was also an answer from one of those persons. And yeah, so it depends, right? But having this discussion is what matters to me.
Right,
in this approach, we can have this discussion.
Then you kind of had this saying that we have this like whiteboard thing and these concerns, and the only thing we do is just adding new boxes, but without changing them, right? Like if you look at this and then you decide, okay, this is one concern, I have it here, and then someone comes like me and saying like, hey, there's 2 concerns. And how often in your practice that happens that you have to actually change? So it doesn't work the way kind of you advertised.
It happens. It happens.
So how often? Like
yeah, pretty often, to be honest. So this is just for presentation purposes, and many times it's like that. So this kind of experience is like that. But of course, sometimes we want to change it because we rethought the whole strategy for this one component. We are splitting it into 2 smaller components, and then compiler helps us with the interpretation, right? Because this is what we really needed. We changed this set of operations, split into 2, and then the compiler will help us with the places that it's used and handlers that we provided.
And who's there to stop you from like splitting that to 1-line programs?
I know, code review, other programmers.
Okay.
Yeah,
because like I mean, if you think you can go like nuts and just get like 25,000 programs each, 1 line long, and then how do you code that all in your head, right? Like how they. So
the whole thing is, I probably wanted to tell you that, but I missed that point. Is that the complexity is still there, right? It's like with microservices. We are splitting that into small microservices, and they are very easy to think about, but the complexity is there. So in this approach, we are just moving the complexity into one place when we can, isolate it from each other. And this is what you are talking about right now. So we still have this complexity, but it's not spread across all the components. It's just in one place, and we can have different strategies to deal with that. And that's where the programmers, the developers are coming into. This is the thing that we need to resolve.
Yeah, thank you.
Sure. Thank you very much, guys, and see you in the hallways.